All right, let's talk about something that happens to every single one of us in data analysis. You know that moment? That critical roadblock where your data is just messy. It's imperfect. It's not playing by the rules. So what do? Well, today, we're going to unlock a really powerful statistical tool that's built for exactly that kind of reality. It's called the Kruskal-Wallis test. So picture this. You're the one on the hook for a huge business recommendation. You've got the data, but man, it is not clean. It's skewed, it's got outliers all over the place, it is anything but normal. All your standard tools, your go-to playbook, totally useless. And a decision needs to be made. What's your next move?
Okay, so the classic move here for comparing three or more groups is the one-way ANOVA, right? It's a powerhouse, for sure, but it's picky. It has to have data that's normally distributed. But what happens when your data is, real-world data? We're talking customer satisfaction scores, ranked preferences, performance data with those crazy outliers. If you try to force ANOVA on that stuff, it can lead you way, way off course to totally wrong conclusions. And that, right there, is the analyst's dilemma.
So yeah, that's the dilemma. You've got this non-normal data, and your trusty ANOVA has basically thrown up its hands and walked away. But look, this isn't a dead end. Not at all. It just means you need a different tool from the toolbox. A really elegant solution that was built for this exact situation.
And that answer is the Kruskal-Wallis test. I want you to think of it like the rugged, all-terrain vehicle of stats tests. Seriously, ANOVA needs a perfectly paved, smooth highway to work. But Kruskal-Wallis? It just thrives on the muddy, bumpy, messy data that we actually find in the real world. Okay, so here's our game plan for getting a handle on this tool. First, what is it? Then, what are the rules for using it? We'll take a look under the hood to see how it works. And, this is a big one, we'll learn how to interpret the results correctly. We'll walk through a real-world example and then finish up with the key takeaways you can start using right away. All right, let's dive in. First things first, what is this test and why should you care? So at its heart, the Kruskal-Wallis test is what's called a non-parametric method. All that means is it's a way to see if there are real, statistically significant differences between three or more groups. And that key phrase, non-parametric, that's its magic. It means the test doesn't care what your data's distribution looks like. It doesn't have to be a perfect bell curve. This gives you an incredible amount of flexibility. And this is where it gets really interesting when you put it side by side with ANOVA. See, ANOVA looks at the actual raw numbers and compares the means or averages. And that's why it needs that clean, normal data. But Kruskal-Wallis, it does something totally different. It works with the ranks of the data. This is its superpower. It literally ignores the raw values and just looks at their order. That's what lets it handle pretty much any kind of data you throw at it, making it just perfect for that messy, real-world stuff we were talking about.
But, just like any powerful tool, you can't just use it without knowing the rules. To really get the most out of it, you've got to understand the rules of engagement. So let's go over the main assumptions.
And honestly, these are pretty straightforward. Your samples have to be random, and they need to be independent from each other. Simple enough. And your data, it just needs to be at least ordinal. All that means is you have to be able to rank it. Think about it. A 1 to 5 star rating system, that's ordinal. Employee performance tiers like meets expectations or exceeds expectations, yep, that's ordinal too. Now, this is a really important point. Don't forget this one. Kruskal-Wallis is specifically for when you're comparing 3 or more groups. If you've only got 2, there's another tool for that. It's kind of like its cousin, the Mann-Whitney U-test. Okay, and what about sample size? This gives us a great rule of thumb. As you can see, if you have fewer than 5 in a group, yeah, probably don't use it. The math gets a little shaky. Once you get into the 5 to 9 range, it's okay, but kind of borderline. The sweet spot really starts around 10 to 19. That's generally reliable. But if you want to be rock solid, the gold standard is 20 or more per group. That's when you know your results are really robust and trustworthy. So we keep saying this test uses ranks instead of raw data. Let's actually pop the hood for a second and see how that simple idea is what gives this test all its power. Okay, so here's the absolute key. By taking all your data from all your groups and just turning it into one big ranked list, the test basically neutralizes outliers. Think about it. A crazy high value doesn't matter if it's 10 million or 10 billion, it just becomes rank number 1. Its actual size doesn't get to skew the whole analysis. And that is a huge, huge advantage over a test like ANOVA that's based on averages. And the actual process? It's really just a simple, elegant logic.
You pool all the data together, you rank it from smallest to largest, then you add up the ranks for each of your original groups. That's it. What you're really looking for is whether the high and low ranks are spread out pretty evenly, or if one group is hogging all the high ones or all the low ones. The test statistic, that H value, is just a way to put a number on that observation so we can make a clear decision.
Okay, now we're at what I think is the most important part of this whole thing. It is super easy to run this test in any software. But interpreting the result correctly, that's what separates the pros from the amateurs. There is a critical nuance here that a lot of people miss.
This quote right here just nails it. A lot of people, and I mean a lot, will tell you that the Kruskal-Wallis test compares medians. And look, that's not just an oversimplification. It can be flat out wrong and misleading. What the test is actually doing is testing something called stochastic dominance. I know, fancy words. So, what on earth does that mean for us?
Well, it means this. When you get a significant result, all it's really telling you is that the distributions of your groups are different in some way. Yeah, that difference could be because the medians are different, but it could also be because one group is way more spread out than the others, or maybe their fundamental shapes are just different. So here's the big takeaway. Please remember this. A significant result is not the answer. It's the start of your investigation. It's a big flashing sign that says, hey, dig deeper here. Your job is not done until you have plotted your data to see why it's different. Is it the median, the spread, the shape? That's where the real money is. That's where the insight is hiding.
All right, enough theory. Let's make this real. We're going to walk through a quick example about operator training at a manufacturing company.
So here's the setup. We've got 4 different training facilities. And the big question is, are they all equally effective? So our starting assumption, the null hypothesis, is that, nope, there's no difference. The test scores are basically the same across all 4. The alternative hypothesis is that, at least one of these facilities is different from the others.
Okay, so we run the numbers, we calculate that H statistic based on the ranks of all the test scores, we get our number. Now, we compare our calculated number to the benchmark, which is a critical value from a chi-square table. For this test, that benchmark is 7.81. And as you can see, our number sailed right past that threshold. It's clearly bigger. And because our test value is higher than that critical value, the decision is easy. We reject the null hypothesis. In plain English, we have solid statistical proof that there is a significant difference in how effective the training is across these 4 facilities. And just like we talked about, the job isn't done. The very next step is to figure out which facilities are different and start asking why.
All right, let's wrap this up. What are the big strategic takeaways you need to remember so you can use this tool effectively?
Let's boil it down to 3 key things for your toolkit. First, the trigger. Anytime you have 3 or more groups and your data isn't normal, your first thought should be Kruskal-Wallis. Second, the superpower. Remember that it uses ranks, which is your best defense against misleading outliers. And finally, and most importantly, the rule. A significant result doesn't mean you're done. It means it's time to start digging. You have to visualize your data to understand why things are different.
So there you have it. You now have a solid way to take messy, imperfect, real-world data and turn it into a real strategic asset. You can find that signal in the noise where other people might just give up. So the real question isn't just about what insights you're going to uncover. It's about what kind of competitive advantage you're going to create with them.